This video is a tale of two phases, ferrite and pearlite, the two room temperature equilibrium phases for our line pipe steels. As Professor Krauss from the Colorado School of Mines used to say quite often, in the beginning, there was austenite. Austenite is the high temperature phase for our line pipe steels and is also the phase where typically a lot of the deformation takes place, the hot rolling. And then that austenite cools to form ferrite and pearlite. So if we have a relatively low carbon content, like most of our line pipe steels, when we cool, we first form ferrite when we cross this boundary for the two-phase region, austenite plus ferrite. And so ferrite grains nucleate and grow, and we end up with a final microstructure of ferrite and pearlite that looks similar to this image on the left. If we increase the carbon content to 0.76% carbon, what we end up with is, at that eutectoid composition, is a microstructure that's made up of entirely pearlite, because the reaction that takes place for the 0.76% carbon is austenite to ferrite plus carbide in the lamellar arrangement called pearlite. Okay, so let's focus just for a moment on this low carbon alloy that's more similar to our line pipe steels. So again, why is there more of the ferrite phase? Well, it's because for the low carbon content, we first hit this ferrite boundary, and so ferrite nucleates and starts to form from the austenite grains, and then we later hit the pearlite boundary. So under equilibrium conditions, the ferrite will form first, and then the pearlite will not form until after we cross under 727 degrees Celsius. So then that pearlite forms. The ferrite forms first, and then the pearlite forms from the remaining austenite. So I've brought in here another plot to help us understand what's happening in terms of temperature versus phase fraction. So as we cool from austenite, because in the beginning there was austenite, here's the line for austenite, and here is 100%. So our microstructure at these high temperatures is 100% austenite. Then as it cools, what happens right here? That's when this alloy hits this phase boundary, and it now becomes favorable for pro-eutectoid ferrite, marked by this line, to begin forming. So originally we had 0% pro-eutectoid ferrite because it was entirely a microstructure made up of austenite. But then the material cooled, and we started forming more and more pro-eutectoid ferrite at the expense of austenite. So the austenite's going down, and the pro-eutectoid ferrite is going up. Eventually, we get all we're going to get. But then we hit another important temperature here, where now we are doing what? We're hitting another phase boundary. And so now our remaining austenite, so we only have a little bit left here. I'm going to draw a square. We only have about 10% of our microstructure remaining as austenite here. okay, because 90% of it has converted to ferrite. Here, I'll show over here. We have about 10% remaining austenite. But now, that remaining austenite converts to ferrite and carbide in a microstructure called pearlite, a constituent called pearlite. So since ferrite grows first, let's talk about the different appearances or allotriomorphs of proeutectoid ferrite, grain boundary ferrite that can form. So up here in the upper left is kind of our familiar polygonal ferrite, where ferrite grows in kind of a blocky shape on the grain boundaries. And in this microstructure, the remainder internal to the grain formed pearlite. On this lower left microstructure, the microstructure is almost completely made up of pearlite, but there's ferrite just lining the grain boundaries. Probably won't be a common microstructure seen for our line pipe steels. Lower right, though, is going to be something important to notice. This is called Widmanstatten Ferrite. It's ferrite that grows in a plate shape because of fast cooling that doesn't allow the time for equilibrium ferrite growth, because the ferrite growth depends on diffusion of carbon getting out of the way of the grain boundary. So for fast cooling rates, we might expect this more pointy shape or jagged shape to the ferrite grain boundaries. Then after the proeutectoid ferrite gets done growing, then the Pearlite transformation takes place, which is a coordinated growth of both ferrite. I'm going to highlight the ferrite here on the upper right image, and carbide, the dark phase here. I thought this was a pretty image of Pearlite growth initiation, the image on the left here, where the pearlite is growing. You can see the lamellar structure, and you can see kind of how it grows from an initiation or nucleation site and grows outward. We have another image on the next slide showing that pearlite growth. So here's a really pretty image of a pearlite colony where you can see where the pearlite started to grow, right in about this region, and then grew outward. And as it grew, the spacing between the lamella of ferrite and cementite continued to expand. Let's review the phase diagram in general and talk about some of the important reactions for steel. Okay, the eutectic reaction is this point right here. That's where liquid forms austenite and iron carbide. Eutectoid reaction is this one right here. So we don't want to get those confused. And that is where austenite forms alpha, or ferrite, plus Fe3C, or cementite, also called carbide. So a schematic of our microstructure in the fully austenite region might look like that. But after the transformation, you get the lamellar platelets of Fe3C, cementite. Sorry, poor color choice. You get the point. And alpha, or the ferrite. And so a real physical micrograph of steel might look something like that. Now our line pipe steels will not be fully pearlitic. They won't be at this eutectoid. They will be hypoeutectoid, below the eutectoid, below 0.76% carbon. And just like the eutectoid steel, they start off in the fully austenitic phase, where all the grains are the same, a single phase region. But then as soon as we encounter this phase boundary, ferrite begins to form at the grain boundaries, and that grows until we get close to the 727 degree Celsius transition temperature to where the austenite reacts and forms the lamellar spacing of ferrite and carbide that we call pearlite. And so this hypo-eutectoid steel, which is going to be similar to a lot of our pipeline steels, might look like this. And it's really important what takes place as the material crosses that 727 degree C boundary, because that's where we need to do our calculation of the phase fractions. So the fraction of alpha, or ferrite, is going to equal the size of this portion of the tie line, S, divided by the full length of the tie line, R plus S. This is called the lever rule. And then the weight fraction of austenite is the complement of that, 1 minus the weight fraction of ferrite. And so the weight fraction of austenite is going to tell us how much pearlite, essentially the weight fraction of pearlite in our final microstructure. And then we can also use the same formula to calculate in the pearlite, in the entire microstructure, how much is ferrite and how much is cementite.